there, and then and hysteresis occur. So only these things that you guys have to, right. This one will not take that much of a time, and yeah, we'll talk about this thing when yeah, this is important one. So this one is important one, and yeah, we'll talk about all these things when we finish those semiconductors. There are okay, so we will start, right. We will start, and Arsalan and we will join. Okay, start. And I have been telling you guys that whenever you guys face any doubts in your any of the chapters, please tell me. Then we can revise those chapters. Okay, so in the last class, we saw that only particular energies or only particular wavelengths or particular frequencies are allowed whose difference matches the difference between the energy levels, right? So this delta E, which is h nu or hc by lambda, this should match with the difference in the energy, right? So these were the difference. Yeah, I have written the energy difference, right? Yeah. So these were the energy difference, and this should match. So whatever emission or absorption is happening, that should match this energy, right? So in the last class, we saw that whenever you are going from higher energy level to lower energy level, so what will happen? Absorption or emission? Yes, guys,
Emission.
emission. So these were some emission spectras, right? And we calculated, so the wavelength of this emission that was already given, right? And we from this thing we calculated what would be the energy difference, and then we matched this energy difference because this should match the energy difference between two energy levels. Then we saw that this D transition, this was its energy difference was matching this whatever corresponding energy we calculated. So yeah, always remember this thing that no other energy that would be absorbed which does not match the energy difference between the energy levels. So that we understood in the last class. Now let us understand about that. Yeah, why did we discard it? Why did we discarded the uh, Rutherford model? Because we saw that the energy levels were not continuous, right? So the elements have different line spectrums, right? Hydrogen-like elements, they have different line spectrums. They are not continuous, right? So all the wavelengths or all the frequencies will have particular energy, right? And those energy should match with the energy difference. So that is why the spectrum would not be continuous, right? So we will understand about what are those line spectra, right? Because we'll get different lines of wavelength, not the continuous line. So in general, what do we see? When the light, when the light is, so whenever light passes through the prism, right? Whenever white light, so whenever, so what is the continuous spectrum that we see in our daily life in general scenario? So let's say we have this prism, right? And then this is the source of light, and this is emitting white light. So whenever this white light falls on this surface, right? So it is divided in seven different colors, right? And this makes a continuous spectrum. So whenever which one would be less deviated? So red one, right? So this is the Vibgeo,
So,
right? So the violet one would be highly deviated, and the red one would not. So it would have a less deviation, right? So this spectrum is not a line spectrum. We will not get lines of violet and purple and all these colors, right? We will get all these different colors continuously, right? So the whatever the spectrum that we get from the white light, that is a continuous spectrum, right? But we see for a different case, when we see that some energy is observed, so then there's a particular frequency that will be emitted from that, right? Or whenever there is emission, so those emission would have a particular energy. So those would be discrete. So there is this beautiful example from which we can understand very clearly what is continuous spectrum, what is the line emission spectrum. Whenever I am saying line emission spectrum, so there would be particular lines corresponding to particular wavelength, energy, and frequency. And whenever I am saying line absorption spectrum, there would be particular wavelength, energy, and frequency of those spectrum. So let me share that thing, right? That would be clear. That is, let me just full screen. Okay, so it is working very slow. Yeah, now it is there. So you see that whenever some white light, right? Whenever some white light, uh, so from this, the lines or the light rays are emitting, and then you pass through some prism. So you will get a continuous spectrum, right? Can you see any black space or any other thing in between those spectrum? You
no,
can, right? So these are continuous spectrum from white light. But whenever we have this hot gas, right? So this hot gas is at some excited state, right? So then it will lose its energy. So this hot gas will lose its energy, but in some specific energy levels, right? It's in some specific energy differences, in some specific wavelength. And let's say if this hot gas was not around, so we had this black spectrum, right? So this black screen. And whenever from these hot gases, the electrons are jumping from higher energy level to lower energy level, so they are emitting particular frequency. And those correspondingly, those frequency, we see some light, we see some lines, and we see that these are discrete. So we have different discrete lines, right? Yeah, so we see, yeah, so we see that we have this line and we have this line. Yeah, so we see that this particular line, this particular line, this particular line. So only these energies are emitted, right? So in this black spectrum, we see particular lines, and these particular lines corresponds to some particular energy. So whenever these emitted rays fall on this spectrum, so they have particular lines, and these lines are called emission spectrum, right? Similarly, similarly, what happens is that we have this bulb, right? We have this bulb, and this is emitting white light, and we place a cold gas between the path of this prism and this bulb. So earlier, what happened was that whenever this cold gas was not there, so we will get continuous spectrum, right? But whenever we place some cold gas in between this white light and this prism, so particular energies are absorbed. Right? So this line, whenever we are getting this black line, so these energies have been absorbed. In the previous case, purple or these red, these oranges line, right? They were continuous. But yes, Mariam, are you saying something?
So your voice.
Understand? Okay, is it? Can you guys hear me now properly? Can you guys hear me now? Is it still breaking?
Yes,
Is
sir,
it
in the middle.
still breaking? Anyways, the internet is working fine here, right? And I can see my router, and yeah, it is not fluctuating. So why this is happening? Because internet maybe I have opened so many browsers and so many the application. That is why the voice is lagging. So can you guys hear me now properly? Can you guys hear me now? Still, hello, can you guys hear me now?
No, sir, it's fine now.
Oh,
It's
good,
yes, sir.
good.
It's fine.
Oh, good. Okay, so what I was saying that let's say we have this white light and we place this prism, so we'll get a continuous spectrum, right? And then I said that we have this hot gas. So let's say that this passes through this prism, and from this hot gas, some energies have been emitted, right? And those have particular wavelengths. So only those kind of wavelengths we will be able to observe in this black screen. So those will have particular lines, right? And these are the energies emitted by this hot gas. And the third case is that I have placed this cold gas, right? So this white light is passing through this cold gas. So some energy would be absorbed by this cold gas, right? And that energy which has been absorbed, it had some particular wavelength, right? So that wavelength will disappear from this continuous spectrum, right? Whatever the energy has been absorbed by this cold gas, that particular wavelength will not be here, right? Because that energy has been absorbed by this thing. So these kind of spectrum, these kind of lines that we are getting, that would be called absorption because it is happening due to the absorption of these energies, right? So is it all these three kinds of spectrum? Is it clear to you guys? What is the emission spectrum? What is the absorption spectrum? Yes. Is it clear, guys?
Yes.
Okay, so now let us write who joined now. Oh, Arsalan, Assalamu alaikum, sir.
Assalamu alaikum.
Yeah, did you hear what we were discussing? Did you hear that?
Yes, sir, a bit I heard.
Yeah, so we were talking about the different kinds of spectrum, right? So generally, let's say some white light passes through this prism, so we'll get a continuous spectrum. But for the case of atoms and yeah, particularly for the case of different elements, we have not the continuous spectrum. We have a discrete spectrum which corresponds to particular wavelength. Only those wavelengths which has the difference between the energy levels, right? So let's say we have this hot gas and some energy is emitted from this hot gas by transition from high energy level to the lower energy level. Then those will have, so this is the black screen, and whatever energy is being emitted by this hot gas, so those have some particular frequencies, and those frequency or those wavelengths we will observe in this spectrum. So this is black screen, and we will observe particular lines. So those lines are called emission spectrum. Similarly, we have this white light, and we pass this through this gas chamber, right? So this gas will absorb some energy, and whatever the energy has been absorbed, that particular wavelength would disappear from this continuous stream. So this, whatever line we are seeing, these are absorption spectrum. Clear, guys? Or is it clear to you, Archana?
Yes, sir.
Okay, so now let us write all these things. So we have line, emission, and absorption spectrum. So let's say we have this hot gas, right? We have this hot gas, right? And some energy has been emitted by this hot gas, and we are observing this on this, right? And we have this whatever this prism, right? So we will see. So this would be a black screen, right? This would be a black screen, and in this, this is a black screen, and we will see particular line, right? We will see particular lines on this black screen, and those will correspond particular wavelengths and particular energies. This would be called, this is hot gas. So what is this emission spectrum? Spectrum or lines observed on the black screen due the emission of particular energy are called line emission spectrum. Right, so this is the emission spectrum. So this happened due to the emission of particular wavelength. Right. Similarly, we have this absorption spectrum. So we have this absorption right. We have this light source, and this is gas. This is white light, and we have this prism. Right, so this is a triangular prism, but I'm making it like this, right? And then we observe this on this screen, on this screen, right? So this would be called the absorption spectrum. So when white light is passed gas and out the rays are observed absorption of particular energies, there will be black line in the continuous spectrum, which are called time absorption spectrum. So these are the two different kinds of spectrum, right? Please note it down, and then we'll talk about the other things. Please note it down.
Done.
Oh, already done. Yes. What about you guys, Aisha and Arsalan?
Yes, it's 2 minutes. On the second
Oh,
part, absorption
yeah.
spectrum.
Yes, yes. So how was your English paper, Arsalan?
Yes, sir, it went well.
Oh, it went
Yes,
yeah.
yes, sir.
Yeah, whenever you guys have completed.
Yes, I'm done.
Done. Okay. So now let us understand about two kinds of energy, right? One is the excitation energy and the corresponding potential and potential. Right. So it's energy, right? So this and this energy that you are providing is called the excitation energy, right? So, so the amount of energy required to move the from lower energy level, e.g., let's say N1, the higher energy level is called. Well, so the first energy level is called the ground state, and all these different higher levels, energy levels, are called excited state, right? So we are moving this electron from lower energy level, which is on the ground level, to the higher excited states. So that is why we call this excitation, right? And this is how much? So this is is to high energy. So this is high energy difference between the high energy and the lower energy. So this would be the excitation, right? And let's say this is equivalent, right? And this is equivalent to some electron and right. So whatever amount of energy you will get, right, change into electron volt. So this is the charge on the electron, right? And this is some potential. This electron volt is a unit, right? Don't get confused with this one. So this is unit, right? And this energy, I'm writing it in terms of so the energy. I can write it as how much? Potential energy. Potential energy is what? QV, right? So I write this charge charge is E and potential is V. Right? This is not the unit. So this is not unit, and this is potential. Right? So let's say I am exciting an electron from ground level to first energy level. Right? So what is the energy difference? Do you guys remember what is the energy difference? What was the energy difference? I guess that was so this is minus 13.6, and then we have minus 3.6, right? What was that? Higher one was, yeah, so this was 3.4, so 10.2 electron, right? So let's say I am giving this electron right? Let's say this is going from, the electron is going from first energy level to the second energy level, right? So delta is how much? That is minus 3.4 minus of minus 13.6. So that is how much? That is 10.2 electron. This is the unit, right? Now what I will do is that I will compare this energy with the potential energy, which is E, right? So whatever potential, whatever coefficient you are getting, so that would be the corresponding potential. So potential would be simply 10.2, right? So this potential would be called excitation potential, right? But the idea is that you have to write this energy in electron volts, right? And just compare the coefficient. So let's say if you are getting minus or whatever 2.5 electron volt, so excitation potential would be how much? That would be simply 2.5. So you guys have to just remember that, right? So this is called the excitation potential, right? We write about the excitation potential is this is nothing but the corresponding potential, the excitation energy is called excitation, right? So you guys please calculate what is the excitation energy from 2 to 3. In going from 2 to 3, and you guys calculate what is excitation energy. The electron is going from second to third energy. So you guys calculate what is excitation energy, and you guys also calculate what is the excitation potential corresponding to this. Please calculate that. And remember, if you don't remember those energy level diagram, then you already know that what is the En, right? En is minus 13.6 z square by n square. So you can use, in place of, you have to use E3 minus E2, right? So in place of n, you can use 3n. So this you can also do. But for the time being, you guys have already the energy level diagrams, right? So use that and tell me what is the value you are getting. What is the excitation energy and what is the excitation potential you guys are getting? Quickly tell me that. Thing. Yes, whenever you guys get any answer, please tell. The electron is going from this to this. Yes, guys, what is the answer? You can directly calculate from the diagram. Yes, Aisha, Maya, Manchana. That is step calculation, right? If we remember the diagram. So you guys have your notes with you right now, right? So you guys can look at your notes and you have those energy level diagrams. Please look at that and just quickly tell me. That should not take that much of a time. Yes, guys, do you guys have some doubts? Hello, guys, can you guys hear me?
Yes,
Yes.
sir.
Yeah, so do you guys have some doubts or did you guys get the answer? Yes, guys, you guys get the answer. Tell me yes or no. Yes, anyone?
Just a second.
1.9, yeah, so excitation energy 1.9 electron volt. Remember electron volt. This is the unit of energy, right? So this is what Aisha has got. The excitation energy is this much. And corresponding potential, what was the corresponding potential? That would be simply 1.9. So this is what Aisha is getting. What are you guys getting? 1.89. Yeah, 1.89. Okay. So 1.89 Mariam is getting, and electron volt. Always remember the unit. This is very important, right? This is not in joules. This is in electron volts. Then only we can write the corresponding excitation potential as 1.8. This is what Mariam has got. What about Arsalan boss? What about you? Yes, sir.
Yes, sir.
Yeah, what did you get? What did you do you have any doubt? Did you not understand the question?
Yeah, so I'm not completely sure what the calculation part. I mean, I
Yeah,
think so.
yeah. So what we have to calculate? How much energy is being? What is the energy difference between these two? That is the only thing that we have to calculate. So that is simply E2 minus E, right? So if we go back to the diagram, what was the diagram? The diagram is this one. So the diagram in going from n equal to 2 and n equal to 3, the energy difference is 1.89 electron. So this is, if we calculate E3 minus E2, E3 is how much? Delta E, excitation energy, that would be because we are going from 2 to 3. So the energy difference we have to calculate 3 to, right? So then this is how much? Minus 1.51 minus of minus 3.4. That is how much? Minus 1.51 plus 3.40. This is how much? 9 and this is 13 and 5. So 8 and this is how much? 2 minus 1. So 1. So this is the energy difference, electron volt. This would be, and this is nearly equal to 1.9. So both answers are correct. So this would be the excitation energy. Clear, Arslan?
Yes, sir.
Yeah. And similarly, because this is already in electron volt, so we can directly write the excitation potential, and that would be 1.9. Right. Is it clear to you, Arslan?
Yes.
Okay, so we can do this question in this way. Or we can do this question in the other way as well, right? So how can we do that? How can we do that? Because let's say if you don't remember this diagram, right? You don't remember this diagram, and you cannot always make this diagram. But you know one thing, and what is that? You know we have to calculate the delta E, excitation energy, going from 2 to third. That is the excitation energy, right? We know that En is minus 13.6 divided by n square. So this would be how much? Minus 13.6 divided by 3 square. This would be how much? Minus 13.6. And there is this z square also, but we are calculating, let's say, for hydrogen. So z is 1. Minus by 2 square, right? So this would be how much? We can take out 13.6 common, and this is 1 by 3 square. And this is how much? We have taken minus common, right? This is minus, so this is minus, and this is plus. So 1 by 4. This is how much? 13.6. Remember, this is in electron. 1 by 4 minus 1 by 9. So this is how much? The LCM of 4 and 9 is how much? 36. And this is 9 minus this is 4. Right. So 13.5 divided by 36. So what would be the answer then? If we cast it to 5 divided by 36. So 1 point again 888, which is 1.89 electron. So from this also, right? From this also we'll get the same answer. And we can also calculate the corresponding excitation potential would be 1.89, and this is the excitation energy. Right. So, and there's on the basis of this thing also, ionization energy and corresponding potential. So, can you guys, and when this atom will become an ion, it's between that atom become an ion. So, you are, oh, what happened? Yeah, what happened? Okay, yeah, so the whole, hear me? Can you guys hear me?
Yes, sir.
Hello, guys, can you hear me?
Yes, sir.
Okay, so let me stop, stop this thing and my internet is again fluctuating. It's still loading. Why? Why, please. Okay, so my screen is not visible to you guys, right? I have shown okay, boss.
No, sir.
No, sir.
Please, yeah, load it quickly. Yeah, it's not, yeah, so it's still not loaded, right? I have, let me stop this and again, so again, yeah, now it is there, it is. Right. So, so what we are doing for the case of this electron which is in initial state, and we are providing it that much amount of energy that the final state is becoming infinity, right? So n is becoming infinity. At that point, the electron is not bounded at all by the atom, right? Then it becomes an ion when this n becomes infinity. So that much amount of energy would be called the ionization, right? So in this case, this is called the ionization. The earlier case was that we were providing some energy and it was going from one energy level to the other energy level. But when that energy level becomes the infinite energy level, so that would be called the ionization. So what is ionization energy? Now you have E infinite and minus of this E1, right? So this would become how much? So this would be simply E infinite is how much, guys? E infinite is how much? Yes, En is minus 13.6 by n square, right? And this is electron volt. So n is becoming infinity. So this is denominator is infinity. So E infinity, that would be simply what? Minus 13.6 by infinity square. So this is 0, right? So 0 minus of minus 13.6 and whatever the n is that, let's say this is second energy level, first energy level, whatever initial energy level that you have, and that divided by this. This would be simply 13.6. And let me also write the z square. Z square divided by n square. So this would be the ionization. And this is in electron volt, right? So the energy, yeah, you guys can write the definition and corresponding potential. Can I rejoin my Zoom? Is glitching? Oh, yes, yes, of course. Yeah, Maria. Yeah, you can. Yeah, you can rejoin. And the corresponding potential would be this minus 13.6 z square by n square volt. So that potential is the ionization potential, right? So is it clear to you guys? Is it clear?
Yes, sir.
Okay, then please these things down. Why this is not speaking? Yeah, so then please note down from here. So please note down. This is the example, right? Going from this energy level to this energy. Yeah, whenever you guys want me to scroll down, please. Yeah, whenever you guys want me to scroll down, please.
Yes, sir, done.
Then please, it's one way is to just look from the energy level diagrams. The other way is to use the formula. Right? Whatever way you can use that, right? And whenever you guys want me to scroll down, please quickly tell me. And today I will finish this chapter. So the last topic which is remaining is the hydrogen spectrum. Hydrogen spectrum that we have talked.
Yes, sir, done.
Yeah, then please. Yeah, I have not written the definition, but yeah, you guys can write the definition, right? The amount of energy required to move the electron from certain energy level to the infinite energy, right? So that would be called the ionization. So the simple way to calculate the ionization energy is whatever the energy of that level is, you just provide that much amount of energy, right? Yeah, whenever you guys have noted, please tell me and then I will tell you the idea.
Gotcha.
Yeah. Okay, so you see that we have this, yeah. So let's say we have this electron which is in the first excited state, right? So this is the ground state. This is the first excited state, and you have other states as well, right? So let's say the electron is at first excited state, and then they will ask you that what is the ionization energy of this hydrogen. Remember, this is the hydrogen atom. So you will directly say that the ionization energy would be 3.4 electron, right? And the ionization potential, that would be 3.4. Clear? Is this clear, guys? Because the energy of
Yes.
this, yeah, energy of this level is minus 13 point, right? And the energy at infinity is 0 electron. So if we provide this electron this much amount of energy, then it will become an ion. That is called the energy. We just directly write the value of the energy level, but we put the positive sign to it, right? Okay, so these were the ideas of energy level diagram, spectrum, and all these ionization and excitation energy. So now let us understand the hydrogen emission section. Right. So hydrogen had, let's say we have this black screen, and in this black screen, hydrogen has this line. So this one and the other one, and then the other ones, and the other one. So these are called, these are different spectrum that we get from the emission, and these have peculiar names, right? So we know that what is the emission spectrum, right? So that would be that electron is going from higher energy level to the lower energy level. So that is the emission spectrum. And we know that this energy will have corresponding wavelength. So how much would that wavelength would be? Right. So that is hc by lambda. Right, guys? Is it correct?
Yes, sir.
Okay, and then we have this, yeah, so we already know that what is this En, right? Not in terms of electron volt, the whole value, right? So what was that? That was, yes, that is, yes, so that was this value that I'm talking. Yeah, this, right. This value that we got, this was in joules, and this is the value that we will, right. So let me just copy this. Yeah, so I will just write this value. So this is ME4 8 h square epsilon naught square. Right. So I will write this value. ME4 8 h square epsilon naught square. That was the value, right, guys? Can you guys tell me that was Z square, right? And ME4 and h square by epsilon naught square. So this was the value, right, guys? Right? Was it
Yes.
Okay, so this is En. So if I calculate, let's say E2, which means that the energy level of that thing is N, right? So if I calculate En2, so that would be how much? That would be minus Z square Me4 divided by N2 square H square and epsilon naught square. Similarly, if I write this is I represent at E2, right? And then E1 is how much? That is minus Z square Me4 divided by N1 square H square and epsilon naught square. And that was 8 also, right? 8 also was there. Okay, and let us put this value in here. So this will be how much? Hc by lambda. And we have this E2, which is minus Z square Me4 by 8 or N2 square and 8 H square epsilon naught square minus of minus Z square Me4 divided by N1 square 8 H square epsilon naught square. Right. So this minus is plus, and these Z square Me4 all these things we can take from, right? So this is Z square Me4 divided by H square epsilon naught square. And this is how much? 1 by N2 square minus minus plus 1 by N1 square. Right. So okay, why this is not splitting down? Yeah. So this is Hc by lambda. And now if we take this Hc in the right hand side, so 1 by lambda would be how much? Z we can take it outside, and this is M E4 divided by 8 H cube and epsilon naught square C. So this is how much? So, and this which is 1 by N1 square minus N2 square. So this thing is called the Rydberg constant, RH, right? This is Rydberg constant, and we can write this 1 by lambda as RH Z square 1 by N1 square minus 1 by N2. So this would be the wavelength of different emission which are happening, right? So the electron is going down from N2 energy level to first energy level, right? And this would be the particular or corresponding wavelength of that spectrum. And this RH is called Rydberg constant, right? Rydberg constant. And this value is how much? That is, I guess, what was that? 1 point, yeah, how much is the value? 0 to 8 to 10 to the power 7, which is Rydberg constant. So this is 1.09 into 10 to the power 7 per meter. So this is the value of Rydberg constant, right? So we see that whenever we go down from higher energy level and to lower energy level, so this will have corresponding wavelength. And this Bohr has defined different spectrum, right? So let's say that the electron is going from all of the higher energy level to the first energy level. So that is called Lyman series. right? What is Lyman series? So the electron is going from higher energy level to first energy level, right? So what do I mean by that? Then 1 by lambda would be how much? That would be RH Z square, and N1 is how much? N1 is 1 and N2 is N, right? So these are, so the corresponding, this would be how much? That would be 1 by 1 square minus 1 by N square. And N can be how much? N can be 2, 3, 4, 5, 6, infinity, right? So this would be called Lyman. When the electron is jumping from second energy level to the first energy level, right? When electron jumps from third energy level to first energy level, fourth energy level to first, fifth to first, sixth to first. So let's say, yeah, we'll talk about that later. So we have this first energy level, right? And then this is the second, this is third, this is fourth, this is fifth, this is sixth, this is seventh, and so on. So all these spectral lines, right? All these spectral lines, this would be called Lyman, right? And which wavelength would be maximum, guys? Can you tell me? Because we know that energy is inversely proportional to lambda. Okay, one moment. Give me one. Yeah. Okay, so this energy is corresponding to the inversely proportional to the lambda, right? So it will emit, let's say the electron is jumping from sixth one to the first one. And let's say electron is jumping from second one to first one. So which wavelength would be, which energy would be larger? Which energy difference would be larger, guys?
Sir, can you
Yeah, so let's say that the electron is jumping from, let's say we have this Lyman series, right? We have this Lyman series, and the electron is jumping from sixth to first energy level, from fifth to first energy level, and second to first energy level. So which one would be larger energy difference? Which would have the large energy difference? Yes. When will it emit the large amount of energy? So when it is coming from the highest energy level to the lower energy level, right? That would be the highest energy, right? You guys can see from this length. So this is the highest energy, right? Let's say this is infinity. So this would be the highest, this corresponds to delta E max, and this corresponds to delta E minimum, right? Is it clear now? Is it clear, guys?
Yes.
Yes, sir.
Yes, sir.
So delta E minimum will have lambda maximum or minimum? What will be the lambda? What would be the lambda? Maximum or minimum? We have this relation. Yes, guys, what would be lambda? See that it is inversely proportional. So if your yeah, energy is maximum, then lambda would be minimum, right? This is lambda maximum because the energy is minimum. So if energy is minimum, lambda is maximum. Similarly, if energy is maximum, then lambda is right. So Lyman series, in Lyman series, you have this lambda max that would be from jumping from 2 to 1, and lambda minimum that would be going from infinity to 1. So these are the two maximum and minimum wavelength, right? And we can also, yeah, so we can calculate this lambda minimum. So lambda minimum would be how much? Lambda minimum is going from infinity, right? 1. So that would be how much? This is for minimum lambda, right? The transition is happening from n is infinity 1, right? So this is the transition. So if we calculate, if we put this value in here, so 1 by lambda minimum, that is how much? RH. And let's say we are calculating for hydrogens, that is 1. Let us put this Z square. And this would be how much? 1 by 1, right? 1 by 1 minus 1 by infinity square. So this part would be how much, guys? This part would be how much? This part would be how much, guys?
Sir, 1 by 1 which is equal to 1 minus 0 or 1
Yeah,
minus infinity.
1 by infinity is 0, right?
Yes, sir.
So
So 1
this,
minus.
yeah, so 1 by lambda minimum is simply RH Z square, right? So lambda minimum would be how much? That would be 1 over Z square RH. So that is your lambda for lime and right? And similarly for maximum lambda, what would be maximum lambda? So that would be, I will directly write, so 1 by lambda max, that would be how much? RH Z square, right? And 1 minus 1 square by 1 by 2 square, right? The electron is coming from second to first. This is how much? This is lambda max RH Z square, and this is 1 minus 1 by 4. So this is RH Z square and 3 by 4. So lambda max would be how much? That would be 4 by 3 RH Z. This would be the maximum wavelength for Lyman right? And there are particular names. There are particular names for different spectrum. So this is called a Lyman alpha spectrum or Lyman alpha line. And that is what? That is when the electron transition from second to one. So that is called the Lyman alpha line. And when the electron transition from third to one, so that is called Lyman beta line. And when the electron jumps from 4 to 1. So then this spectrum is called Lyman, right? And one thing also to note that Lyman series lies in the UV range, right? So they have relatively smaller wavelength, right? They have relatively small. Is it clear? Is this series clear to you guys?
Yes, sir.
Yeah. So the Lyman series you guys have already done in your 10th standard, but we are just extending that one. Please note it down, guys. Please note it down, and yeah. So only the other bracket, Passion, put and yeah. So Diamond, Palmer, Passion, bracket, right. These are the other series that we have to study, but yeah. And if you guys have any doubts, please tell. Okay, so I have written here hydrogen emission spectrum. So this Z would be 1, right? For hydrogen, this would be 1 by lambda RH, 1 by N1 square minus. This would be for hydrogen. I have calculated for general scenario, but yeah, this would be for hydrogen. Whenever you guys have want me to scroll down, please. I guess 15 minutes class will be needed again to complete this chapter. So in the next class, we'll start this nuclei, and nuclei will only take one class. Because in nuclei, we have to only talk about this mass defect and binding energy for nucleon, and then nuclear field energy. So then that chapter will be nuclear.
Sir, can you scroll down?
Oh, yeah.
Yes, sir, can you scroll down?
Yeah.
Done, sir.
Done, everyone.
Done, sir.
So we'll stop here, and you guys please revise this part because these are very small chapters and they carry